And 13.5 is an introduction to some of the things that you're going to look at in calculus next semester. So 13.5 is looking at some ways you can estimate the area under a curve. So we're kind of just going to do an intro here. And then this is something that's going to come up in calculus again, like I said, and then you'll get to go into some of the more interesting stuff. So what if I start out with a graph that we know well? So the graph of y equals x squared. And I say, how can I estimate the area under the graph between 0 and 2? So I guess really what I want to know is between here's 1, here's 2, here's 0, right? I would really like to know what is the area underneath that curve. So that's something you're going to look at finding precisely in calculus. But we can estimate the area. So we're going to do this using rectangles. So I don't know, maybe I should start by just labeling the points. So I have y equals x squared, right? So if I plug in 1, I get 1. If I plug in 2, I get 4. And then, of course, 0, 0. Okay. So what if I draw rectangles in? Like, okay, what if I say I'm going to take a rectangle and I'm going to draw it in here. And then I'm going to take another rectangle and I'm going to draw it in here. Okay, I can find the area of rectangles. So if I found the area of those two rectangles, I would have an estimate for the area under the curve. Now, it would be a pretty big overestimate because I would have included all this extra area. So that would be if I only used 2 rectangles. So what if I used more than 2 rectangles? So the more rectangles I use, the more accurate an estimate I would get of what the area under the curve actually is. So let's see, if I'm going to use, this problem says use 4 rectangles. So I have to look at the total length here. So I'm interested in between 0 and 2. So I have a distance of 2 units, right? So I have to take those 2 units and I'm going to break that up into 4 rectangles, okay? So that means that each of my rectangles, I'm going to have a half a unit per rectangle, okay? In other words, so when I break this up, here's 1, I'm going to have a rectangle, you know, that's at a half, another one that's at 1, another one that's at 1.5, and then another one that's at 2. That way I'll have a total of 1, 2, 3, 4 rectangles in there. So the next question becomes, well, how do I actually draw the rectangles? Because I have some options depending on which endpoints I choose. Like, do I choose the right endpoints, the middle endpoints, or the left endpoints? I mean, let me show you what I mean. So say I chose the left endpoints. That's not what the problem asks me to do, but what if I did that? Then I would start my rectangle here. So my first rectangle would actually have an area of 0. Then I would start here. Here would be my second rectangle. Then I would start here. See how I'm using each left endpoint to be the top of the rectangle? And then I would start here. Okay. So those would be my rectangles if I did left endpoints. So that would be, in this case, that would be an underestimate of the area, right? Because I would have left out all these areas. Okay. So that's one option. I mean, I could choose the left endpoints. Let me show you another one. Let me just leave that blue dot there. So what if I chose the middle of the rectangle? Let me see if I did one like that. Oh, right endpoints, left endpoints. I didn't, I guess, but I could have, so if I chose the middle, for the endpoints, that means I'd start in the middle of each rectangle, and I'd take that to be the height. So here's the middle of the next rectangle. So it kind of depends on what kind of curve you're dealing with as far as what the most accurate choice might be. So I mean, that's another idea, and that actually seems like it might have given me a reasonable estimate. I mean, I'd have some extra areas that I'd be accounting for here, but then I have some areas left out here, 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 and here. Okay, but this time we're going to go with what the problem said, which was use the right endpoints. Then we can see if that's an overestimate or an underestimate. Okay, right endpoints. All right, so I start then at a half. Here's where the rectangle starts, and I go to the right endpoint. So that's where that rectangle ends. So let me label that point. So like, what is f of a half? That'd be a half squared, right? A quarter. So the height of this rectangle is a quarter. Okay, we do the next one. So I go to the right endpoint. So here, that one's already labeled. Okay. So the height there is going to be 1. Okay, then 3/2. I go to the right endpoint, somewhere about there. So what is f of 3/2? 9/4. So I'm not doing the y-axis really to scale here. I'm really just labeling the y values for each rectangle. Okay, then one more. So to the right side, so the y value is 4. That one's already labeled. Okay, so now let me find the area of each of these rectangles. So to estimate the area under the curve, that's going to be approximately, so I need to find the area of each rectangle. So look, the area of the rectangle is the length. That's a half, right? Each rectangle is length a half times the width. So the height, that's a quarter. So I could write this generally like this is f of a half, right? Let me start by writing it like that. Look, here's the next rectangle. The length is still a half. And then the height would be f of 1, right? Because that's the right endpoint. Okay, the third rectangle, length is a half, the height is f of 3/2. Then the last rectangle, its length is still a half, and its height would be f of 2. So that's writing the thing kind of formally, but we already found these values. F of a half was a quarter. That's looking at this rectangle, right? A half by a quarter. The next one's going to be a half by 1. Third one would be a half. What was f of 3/2? 9/4. And then the last one would be a half times f of 2 was 4. Okay, so what do we have? An eighth, a half, 9/8, 2, 10/8, 5/2, plus 1/2, plus 9/8, or plus 2. Did I get that right? Let's see. 10/8. Let me start that over. I think I did make a mistake. Let me do one extra step. Okay, 9/8 plus 1/8, 10/8, a half plus 2. So 5, that's 5/4. Plus a half, plus 2, so the LCD is 4. Let me move this down. Five fourths plus 2/4 plus 8/4. Did I get that right? I think so. So that's 7/15/4. So what is that? That's about 12, 3 3/4, about 3.75. Okay, so let's see. Is this an overestimate or an underestimate? This would be an overestimate, right? Because we've got all these extra areas here, in addition to the true area under the curve, which is this portion. But it's an estimate. So this would be an estimate of the area under the curve. I'm going to note that this would be an overestimate. Okay, now, same thing, but using the left endpoints. Okay, so that means, all right, I still want to do 4 rectangles. So if I'm still doing 4 rectangles, I still have a length of 2, 4 rectangles. Each length, the length of each rectangle would still be a half. So here's 1, here's 2, there's a half, and 1 1/2. But now I'm using the left endpoint, so that means my first rectangle is actually here. It has 0 area. Okay, then here's my next rectangle, using the left endpoints. It's going to stop here though. All right. So then to estimate the area under the curve, that's going to be about, let's see, this guy is a half, but its height is 0. The next length is a half. Look, looking at this rectangle, the length is still a half, right, here to here. But what is the height? So there's that f of a half again. So what was f of a half? F of a half was a half squared, right? That was a quarter. Okay, so this rectangle is a half by a quarter. What's this one? Its length is a half. Its height is f of 1. F of 1 is 1 squared is 1. The last rectangle, its length is still a half. Its height is f of 3/2. F of 3/2 is 3/2 squared, right? 9/4. Okay, so that's 0, that's an 1/8, plus a half, plus 9/8. 10/8 plus 1/2. 5/4 plus a half. So 5/4 plus 2/4, 7/4. So 7/4 is 1.75. So look at this one. In this case, I've left out all of this area. So this guy, I notice this guy is going to be then an underestimate of the area. So I guess that's kind of cool in the sense that, well, I know the real area then is going to be somewhere in between 3.75 and 1.75. But that's not really all that precise. But, like I said, you'll go into it in more detail in calculus. This is an introduction. Here's another function, something other than just a quadratic. Estimate the area under the graph of f of x is 2 over x from 1 to 4. Okay, so I already did the graph, but I mean, 2 over x looks like this. It's a stretched reciprocal function. But I'm only interested in between 1 and 4. So I only graphed this side. So how did I get these values? I plugged them in, like what is f of 1? F of 1 is 2 over 1 is 2. That's this point. F of 2 is 2 over 2 is 1. That's this point. F of 4 is 2 over 4 is a half. That's this point, etc. Okay, so that's how I got that curve. Okay, use 3 rectangles and right endpoints. Okay, so starting, it's only between 1 and 4. Let me get rid of the scratch work. Interesting, so I'm looking only between 1 and 4 here. My goal would really be to find the area under this curve, but I have to use rectangles, so I'm going to be estimating. So now I'm using right endpoints and 3 rectangles. So let me see here. What is this total distance? 4 minus 1 is 3, right? So if the length is 3, the number of rectangles is also 3, then that means each rectangle is going to have a length of 1 unit. Okay, so 1 unit length per rectangle. All I did there to figure that out is figured out the total length and then divided by the total number of rectangles. Okay, so then I want right endpoints. Okay, so that means looking in this region that I'm interested in, between 1 and 3, each of my rectangles has a length of 1 unit. Or between 1 and 4, rather. Okay, so I can see my 3 rectangles in here. There's one there, and one here. But be careful, I have to use the right endpoints. So this would be the right endpoint of this rectangle. So that's the point of interest. Here's the right endpoint of that rectangle. So I guess I need to find that value, huh? Okay. So what is f of 3? That'd be 2 over 3. And then I should be able to set up my sum. So it's not too bad. So to estimate my area under the curve, that'd be approximately, let's see, the length of the rectangle is 1. The height of that rectangle is 1, right? 1 by 1. The next rectangle's length is, of course, also 1. What is its height? Its height is 2/3, right? Next rectangle length is 1. Height is a half. So what do we have? We've got 1, we've got 2/3, and a half. LCD is 6. 6/6, 4/6, 3/6. 10, 13 over 6. That's 2 1/6. Oh, should I get an estimate? I don't know what 1/6 is offhand. Let me see. 2.17. Okay, now of course that's going to be an underestimate because I'm missing this chunk, and that chunk. Looks like it's a little better maybe than our parabola though. So I'm going to note this is an underestimate. Okay. What if I do the same thing but looking at the left endpoints? So I'm still interested in between 1 and 4. So here's my first rectangle. Here's the left endpoint. And the left endpoint. Okay, let me label, let's see. So that's 1, 2. So this rectangle, 1 by 2. This point was 2, 1. So this length was 1. This height was 1. This length was 1. This point was 3 over 2. So this height was 3 over 2. So then when I go to find the area, that's going to be about, so 1 by 2 plus 1 by 1. This is 1 by 2, right? 1 by 2. This is 1 by 1. This is 1 by 3/2. 2 plus 1 plus 1.5 is 4.5. 9 over 2. So this would be an overestimate because I got this chunk, and this chunk. Okay, so the actual area would be somewhere in between 2.17 and 4.5. So I just made note down here that as the number of rectangles increases, the more accurate your estimate of the area is. In fact, if we let the number of rectangles go to infinity, we have the actual area. So I'm just saying there that, I mean, the more rectangles you put, I kind of already said this, but like what if you cut this in half. There's your first set, cut it in half again. I think that's what we actually did. Then what if you cut in half again? Like then, when you drew your rectangles, you'd be here, right? So you'd be closer to the curve. I'm just kind of not being too precise here. I just want to point out how this is going to work. So if you broke up again even there, then you'd be closer to the curve. Like, look, you could even cut these rectangles in half again. Then you would go here. Your next one would start there. See how I'm getting closer and closer to the curve each time? I'd have less extra area each time I cut those rectangles in half. Something like this. Oops. Here, but you get the idea. So each time I cut those rectangles, I'd actually be closer and closer to the curve itself. So if you let the number of rectangles, say, go to infinity, that means you're actually going to be right on top of the curve instantaneously. So that would be a way of actually finding the area under the curve precisely. So this is what's coming up in calculus. And then you're going to go into the concept of the antiderivative, okay? The integral.